Right, so in 2018 the Russians created a nuclear battery. They actually followed work done by Bristol University, where what they did was take the carbon rods out of a nuclear reactor and turn it into a battery. Now the carbon rods are used to cover the nuclear fuel rods, because the nuclear fuel rods put out lots of neutrons. Some of those neutrons are just fast moving, some of them are hot. You want the hot ones inside, you want to get rid of the fast moving ones. So the fast moving ones go into the graphite that surrounds the rod, absorbed in the graphite, and changes carbon 12 and 13, which is pretty innocuous, into carbon 14, which is radioactive. So of course when they decommission a nuclear reactor, there's a ton of radioactive graphite kicking about. What Bristol did was take that graphite, sublime it, that is turn it directly from a solid into a gas, use chemical vapor addition and create a sheet of radioactive diamonds. That's kind of cool if you think about it, because diamond actually is a semiconductor when it's in that state. So making a sheet of radioactive diamond and putting another semiconductor device on top of it means that they were able to make a battery out of it. And this battery works in pretty much the same way as a solar cell does, by emitting these alpha particles or beta particles, knocking off electrons and driving a current. When something decays, it decays back from carbon 14 to carbon 12, or whatever it is doing that way, and it does it by the emission of alpha particles, which are helium, or beta particles, which are electrons. Now, diamond emits an awful lot of beta particles, so it's called beta voltaic. Other materials emit an awful lot of alpha particles, and they're called alpha voltaic. Both of these have been used in batteries before. It was in 1970 when the first nuclear battery was commercialised, and it was used in pacemakers. Because it was used in pacemakers and because it had an 88-year lifespan, then you never replace it. Normally a pacemaker is replaced through surgery every 5 to 10 years, but these nuclear ones that were put in the 1970s never need replacement. They're 88 years lifespan and you're done. You would be in your grave longer than it would take for this battery to run out. Now that's only pacemakers. They use plutonium actually. And the half-life of it is what it gives it its power. Now, when you think about nuclear batteries, you probably think about space shuttles, that sort of thing. Really high-end, really dangerous stuff. And that's very true, they are. But they're also exceedingly interesting because they last such a long time. In themselves, they have a low energy density during a short period of time, but because they last for such a long time, they've got huge amounts of energy density. And of course, we've got quite a lot of nuclear waste. So being able to use that nuclear waste in a productive manner like that is what's got everybody kind of excited, particularly as Bristol and the Russians have come up with this diamond battery. And that's got a lot of people's imaginations going. Now, I think we're going to make our own nuclear battery because they're surprisingly easy to make. You only really need three things. You need a smoke alarm, the ionisation type, and you need a transistor. Now I'm using the 2N3055, 2055, what is it? 3055. So I'm using a transistor, the 2N3055, because these things can be used as straightforward solar cells. If you chop off that top, connect to the collector, which is the tin here, and the base of the output legs, then you'll get yourself a solar cell when you pop that into the sun. Because a nuclear battery needs an ionisation source and a semiconductor junction. And the only other thing it needs is a healthy disregard for your own safety and that of any future children who may be born with two heads. If you've got those things, then you can make your own nuclear battery actually really easily. Now, what's inside these things is an NPN junction. These two are the N materials and this one is the P material, and you want the NP junction. Now, between the base, which is this leg here, and the case is the NP junction that's lying on the top. So it's the one that's going to perform the best. If you want to make a solar cell, you do exactly the same thing, just shine it in the sun, and you'll get the most out of that particular junction, although they'll all work. Anyway, let's take this apart and have a look inside. That's what it looks like on the inside once we've got it open, and that tiny square is the semiconductor material, and there's some delicate wires going to each pin. Got it exposed to ambient light, and you can see on the pip it's about 1/4 volt. If I cover that up, then obviously the voltage drops off because I'm having a light response. Got myself a torch, shine that on, and there we go. The voltage jumps up. So that's the transistor having a photovoltaic effect. And like I say, alpha voltaics and photovoltaics are not too different from each other. So now what we need to do is take our source out of here. Which ionizing alarms use americium-241 as their radioactive source. They collect the smoke, ionize it, and that's how the smoke alarm actually works. But inside there is a small piece of americium-241. Now, americium has a half-life of something like 432 years. So just like that little square in the photovoltaic is only going to produce about 70 microamps or so, it's not going to produce a huge amount, but it's going to do it for 430 years, and that's what makes them incredibly energy dense. Okay, so word of warning, this is for experimentation purposes only, so that I can show you what's going on, and it's meant for education and illustration, and I'm doing it so you don't have to. So if you go ahead and do this yourself, well, on your own head be it. It's purely for educational entertainment purposes. Take your smoke alarm apart, you'll have this big black thing in here. That's where the actual material is. That's just a piezo buzzer. If we take that black thing off, you find this red thing here, and right in the centre there is the americium emitter. Now it's held in a case covered with foil and covered with a ceramic, and so behind it actually the alpha particles can't actually escape. It's only from that little dot there that all the alpha particles are being fired out. So if I pointed at you, you're the one getting the radiation, not me. So I've got my radioactive material and put it on a stick. So it's at the moment emitting alpha particles only in that direction, so I have no intention of staring at this like that or pointing it at my genitals. What I'm going to do is keep it pointing outwards. Now, we have our transistor here, we've got our pip, and you can see it's reading about 1/4 volt, and that's because of the ambient light. If I stick my finger over there so that we can see that we got no light going in there, and it drops right down to what is more or less 0. And that's because I'm about to cover it with this. So anything that produces is going to be because of the radiation that's coming off of there, not because of the ambient light. So there we go, we successfully made ourselves a nuclear battery. It was alpha voltaic, and it was using the same principle as photovoltaic cells do by hitting that NP junction with alpha particles and driving a current. And that and beta voltaics are the basis for most of the research in nuclear batteries at the moment. And as I say, this is a demonstration, and we now have ourselves a nuclear battery. It didn't give out a huge amount, but it wouldn't do. But with americium, it will last 432 years, so that is going to be pretty energy dense over the lifetime of the battery. Anyway, I hope you enjoyed the video. That's how you make your own nuclear battery, and if you did, please remember to like and subscribe.